This lecture 10, see, lecture 10, part 1. The objective of this lecture is to obtain the determinant of the metric. Okay? You see that's a very important in several applications in classical mechanics, special relativity, general relativities. It's very useful. Okay, I will show here for you. Now, from the previous lecture, don't forget, you see, I recorded lecture 1 to lecture 9. See, this is lecture 10. From previous lecture 8 and 9, see, I arrived in detail lecture 8 to see here, lecture 9. I call relation 1 and relation 2. Now, x dot y, okay, x is the cross product between A and B. Y is the cross product between C and D. Now, from this relation 2 here, lecture 9, I will let A is equal C, this is equal A1, B is equal D, is equal this cross product here, A2 cross A3. Why I'm using A sub 1, A sub 2, A sub 3? Because they consist in determining the metric tensor, okay, which I'll be talk in later videos, okay, later lectures. Okay, I want to show that this mixed product, attention now, here's a mixed product. I have a scalar dot product, and also I have a cross product that you call mixed problem. Mixed. Then I want to show that this mixed product is equal to square root of G, and G is the determinant of Gij. Gij is equal to Gji, because I will show this later, okay, deriving other lectures, other subjects. So Gij, Gji is a dot product between Ai and J. Just assume that, okay? Then you see clearly why I, in this case, I define, say, Gij this way. Now, let's continue here. You see, the objective, don't forget, is to show that this mixed product is equal to the square root of G. And G, repeating, is the determinant of Gij. Gij is a metric tensor. I'll call this relation over here as lambda. You see? Observe that A1 dot A2 cross A3 is a scalar. So this is a scalar, the same product, the same term here, same factor is better. Okay, let's continue just carefully. Lambda, I will define G11 as the dot product between A1, A1. I define G11. Okay? Now, you see this relation here, okay, it came from relation 2, is lecture 9, which I set A is equal C is equal A1, B is equal D is equal A2 cross A3. Okay, that's why I want to show this relation. Now, you see lambda is G11 by definition, okay? And because you can see that AI dot AJ is GIJ. So this is A1 dot A1. And this is a relation obtained, attention now, just plugging A is equal C, B is equal D is equal A2 cross A3. I just plug it in the relation 2. Then I obtain, okay, this row here, okay? So it's quite easy, just substitute, okay? And again, I'll repeat that these identities I already derived, you see, in lecture 8, in lecture 9, okay? Part 1, see? So let's continue. I call this the green, the phi. Okay? Phi is this term over here. Is the dot product between the cross product A2 cross A3 dot A2 cross A3 and minus x dot y. Okay? X dot y, you see here, it comes from the equation in this case, okay? The relation, let's say the lecture 9, relation 2. X is A cross B. Y is C cross D. Don't forget that I'm substituting, you see? A, C, B is equal D, A is equal C, B is equal D, okay? And this relation here. So, let's expand this scalar phi. Okay? Don't forget that. See? Again, phi is the dot product between this vector and the same vector, A2 cross A3. Now, I use the identity, okay? The identity that, again, I already derived, you see? Then this identity is equal A dot C, B dot D, minus A dot product, D and C with D. That's right, lecture 8 and 9, attention now, okay? Lecture 9 is a triple product, which is not the case over here. Now, you're going to talk about triple product later in this lecture, okay? Now, that's phi. See, you can see easily, just substitute that I call A2 dot A2 as G22. You see aqui? J22, by definition, okay? And G dot A3 dot A3 is G33. Is that over here? Now, A2 dot A3 is G23, is here. And here's G23, that's why I have a square here, okay? So, this is my fourth equation, okay? Now, I substitute because you see, the color, okay? It makes clear, okay, this development. So I substitute phi on this relation here, okay? But phi now, okay, is the right-hand side of it, okay? So I substitute 4, you see, into, into 3, okay? This equation, relation 3. Attention, lambda is what I want. You see? That's what I want. This I already developed, G11, and now my focus is phi, okay, the green one. I got the green one, then I substitute here. You see, then I have clearly, this is the blue one. You see, that's the green one, okay? So what's left, x dot y. I call this expression 5. Okay? Now, you see, I expand this, I expand G1, this G1, and I expand the green one. You see the green one here, there's the blue. Now, I want to work, to focus on this X over here. It's interesting. X dot Y is X is A cross B. Just look, before I showed that. And Y is C cross D. But you see it that X is identical to Y because A is equal C and B is equal D. Okay? I'll show you, it will be appear here. See, look at here. A is equal C is equal 1. B is equal D is equal this dot product here. Okay? That, I'm sorry, this cross product here. Okay? Then easily I substitute A and C, B and D, just in the expression, okay, for X. Okay? Obviously for X and Y, because X is equal Y, is identical to Y. This is X and this is Y. Now, you see, it appeared the triple product here. The triple product. Why? Because A1 cross, you see, I have A cross this here, this cross here, the B is already a cross. So that's why I have a triple product. That's easy to follow. See? I advise you to put a blank paper on your side. Okay, just write down this. It will be quite easy to follow. Okay? And the colors will help a lot. Now, from the triple product, see lecture 8. Okay, I derived this expression here, this identity. It was derived there. See, lecture 8. Till now, we talk about we are using, okay, lecture 9. Okay, but now it appeared the triple product. Then I'm going to use lecture 8. So the lecture 8, A cross B cross C is identical to A dot C B minus A dot B C. Attention now. You see, X dot Y, okay, is a scalar quantity. Okay, lambda is a scalar quantity. Okay, now, attention now, because you see, this identity, look, A1 dot A3 is a scalar. A scalar, okay, this is a vector, A2. Again, A1 dot A2 is a scalar. So a scalar, a vector, so this term over here is a vector. This term over here is a vector. This is not a surprise because the triple product, okay, it is a vector. See, so X is a vector. Okay. Now, then I came up just easy. You see, A1 dot A3 is G13. A1 dot A2 is G12. I just plug in here, you see. So I have X. Since X is equal Y, is identical to Y, now it's quite clear that this dot product, I just repeat. You see, this is X, and this is X also, because it's Y. Y is identical to X. Now, you see this dot here? I will have 4 terms, okay? This one will be applied to these 2 over here. This one will be applied to these 2 over here. So I'll have four terms here. Okay? Just easy algebra. Okay? Now, then I will have, Okay? Attention now. For instance, A2, G13, A2, dot G13, A2. A2 dot A2 is G22. That's why it appeared, see, easily, okay, that A2 dot is G22. That's easy, no problem here, okay? So you have to pay attention. First, A3 dot A2, see, this will be G32. Since it is symmetric, it's the same as G23. So it's quite easy here to develop this. Now, so then I'll get x dot x. Actor is x dot y, since in this case, I imposed the y is equal x, then I'll have this expression. Now, substituting relation 6 into relation 5, my goodness, it's quite easy here. Okay? Let's find the equation 5. You see the equation 5? This I got, Now I derived x dot x. Okay? So that's why I will plug on equation 5. See? This gives my lambda. Don't forget lambda. This is what I want. Okay? This is a dot. This is a mixed product square. And then the G11 phi that I already get. And now x dot x. I just substitute by x dot x. Is the whole expression here. Okay? It's the whole expression. Okay? Again, the colors will help a lot. See? No confusion. Now, lambda is equal. You see this minus here? So I have to change sign. Okay? This within the parentheses. Okay? Now I already changed the sign. Now I can see clearly, okay, that lambda is a mixed product, it's a scalar quantity, square. So this here, the whole, the design here, okay, I can represent this determinant. Okay? If you don't believe, okay, you expand the determinant over here, then you lead to this expression. Okay? So lambda is this square, is equal to determinant of Gij, okay, which I call G. Okay? So this mixed product will be square root of G. Attention now, okay? Because this expression over here, this relation, will be used. Okay? Now, I will have more than 500 videos, okay, about what I'm talking about. It's a lot of work. As I said, I have more than 500 written pages. You see what I mean? Just to reach my final objective is the Einstein field equation. And this here will be our good friend. See what I mean? This is square root of this, the determinant here, the determinant. Okay? That's it. Now, here I'm just emphasizing, okay, the importance of this G. Okay? This important relation in differential equation, special relative, general relative. Differential geometry also is applied in extrinsic geometry. In general, when I say extrinsic geometry, it's our classical. That's It's a classical math. This is in general I use for R3, okay, in 3 dimensions. See? Intrinsic manifold, just use both. I could write for R3 and R4, the space-time. That's why I put special relative, general relative. I use in R4. The coordinates are the CT, the time, X, Y, and Z. That's why I have this. Okay? So, that's a very important now. Then next, I will derive for part 2 is the properties of the metric. Okay? It's very, very important. Okay? Which will be applied to the Cartesian coordinates or general coordinates. Okay? Any is a curvilinear coordinates. In this case, it will be any curvilinear coordinate, which a cylindrical coordinate and spherical coordinate are particular case of curvilinear coordinate. We're going to talk in general, because of the space-time in general relativity, we work with general curvilinear coordinates. That's and you also could apply to spherical coordinate, but in general, the derivation is for curvilinear coordinates in R4. See, that's it.